Good morning, everyone. Today I am going to deliver a lecture on 4th semester mathematics paper 4 Algebra Unit 3 Lecture 11 on Principal and Primordials and Quotient Rings by Dr. P. Ramulu, Head Department of Mathematics, MVS Government Arts Science College, Mahabubnagar. What is principal ideal? Let R be a commutative ring with unity and A belongs to R, then the ideal AR is that R belongs to R of all multipliers of A is called principal ideal. It is generated by A. It is generated by generator A. Therefore, generator A equal to AR is that R belongs to R. Or other definition, let R be a commutative ring with unity A belongs to R, then the set AR such that R belongs to R, it is denoted by generator A, is an ideal of R, is called principal ideal of R. That means a ideal which is generated by some element is called principal ideal. Example, I am taking that Q comma plus comma dot, 1 belonging to Q. Generator 1 equal to what happen? AR, nothing but A equal to 1, here 1 into R equal to R only, such that R belongs to Q. That means R equal to Q. So Q is generated by 1. The ideal Q is generated by 1. Therefore, Q is principal ideal. I am taking that Z comma plus comma dot, 1 belonging to Z. Generator 1 nothing but 1 into R nothing but R. R belongs to Z, that equal to Z. Generator 1 equal to Z, therefore the ideal Z is generated by 1, therefore Z is principal ideal. If I take 2Z comma, generator 2 nothing but 2 R such that R belongs to Z, that equal to 2Z, so the ideal 2Z is generated by 2, but 2Z does not have identity element. That means our ring with unity, 2Z is ideal but is not ring with unity. That means 2Z does not containing identity element 1. Therefore, 2Z comma plus comma dot is not principal ideal. Similarly, 3Z comma 4Z comma 5Z comma data up to so on are not principal ideal. Why? Because it is generated some elements, but these ideals does not containing identity element. If I take Z6, Z6 equal to 0, 1, 2, 3, 4, 5. Generated 1 is equal to 1 half is that R plus Z6 is equal to Z6. So that means Z6 generated by 1, therefore Z6 is principal ideal. So I am taking the generator 2 in Z6, so that means generator 2 equal to 0, 2, 4, 6. So generator 2 is an ideal of Z6, but it is not principal ideal. Why? Because it is generated by 2, but it does not contain an identity element to 1, therefore it is not principal ideal. Similarly, we can verify that R complex comma dot and C complex comma dot, generator 1 equal to R such that R belongs to R, 1 into R equal to R only, that belongs to R, and also generator 1 equal to 1 into R that equal to C. So that means these also principal ideals, R complex comma dot and C complex comma dot also principal ideal. Generally, Zn addition model multiplication model is a principal ideal, which is generated by generator 1, therefore it is principal ideals. Already, for example, every field is a principal ideal. Every field is principal ideal. So, factor ring or quotient ring. Factor ring or quotient ring. Let R be a ring and A be subring of R, then the coset R by A, the factor set, whatever may be. The factor set, right, the quotient R by A equal to R by S is that R plus is that R plus R is a ring under the operation. First one is small s plus A plus small t plus A equal to s plus t plus A for all s comma t plus A belongs to R. Here my A is ideal. I am taking that where A is ideal, and other operation s plus A into t plus A equal to s t plus A. So with respect to these two operations, R by A is ring. I want to show this is ring. This is a factor ring. So I want to prove this. Let R be a ring, A be a subring of R. Let A be an ideal. So let A be an ideal. what is our ideal? If a comma a, r belongs to r, example a r comma r belongs to a and a minus b belongs to r, then we have to prove that r by a is subring by using these properties. So with respect to the following given operations, to show that r by a is a abelian group, for that we have to show that closure, associative, identity, inverse, abelian properties. First of all, I want to show that closure property. So closure property is similar to the hypothesis only. So it is clearly it satisfies closure property by hypothesis only. S plus a, t plus a belongs to r by a, s plus t belongs to r by a. Already by since hypothesis only, it is by definition it is hold. So to show that it is I want to show that associate property. S plus t comma s plus a, t plus a, p plus a belongs to r by a. I would taking three elements. So s plus t plus a equal to p plus a. S plus t nothing but s plus t plus a that equal to p plus a. You can write as s plus t plus p plus a. This is similarly s plus nothing one element to p plus, so same definition you can apply here. S plus t plus a. S plus t plus c plus a equal to, see, s plus t plus p could write it as s plus t plus a. Why? Because R is ring, R satisfies associate property. This s comma t belongs to R. It is that means R is a ring, satisfies with associate property. So similarly, it can write as s plus t plus t plus a. This can write as s plus t plus s plus a plus t plus a plus p plus a. Therefore, R by a is associative property. Okay, satisfies. To show other identity property, I am taking that s comma 0 belongs to r, s plus a comma 0 belongs to r by a, s plus a into 0 plus a. I am verifying whether equal to it. So according to definition, s plus 0 plus a, s plus 0 plus equal to s. So since s plus 0, s is a ring, sorry, r is a ring, s belongs to r, therefore small s here, s plus 0 equal to s. So since r is satisfies identity property with respect to addition, so this means s plus a plus 0 plus a equal to s plus a. Similarly, we can verify that 0 plus a plus s plus a equal to s plus a. Therefore, s plus a plus 0 plus a equal to 0 plus a plus s plus a equal to s plus a. 0 plus is the identity element in r by a. Similarly, s comma minus belongs to r, as s plus minus s belongs to r by a. I am taking that s plus a plus minus s plus a. By definition of addition, you can write s plus factor ring. So s plus minus s plus a, s plus minus s is equal to 0. So similarly, s plus equal this is equal to 0 plus a. Similarly, we can take minus s plus a, s plus a that equal to 0 plus a. So it is minus s plus a is inverse of s plus a. R by a satisfies inverse property. Abelian property, s plus a plus t plus a equal to s plus t plus a. T plus s plus a equal to, I am writing as t plus, here by definition only s plus t written as t plus s, since r is abelian. T plus a equal to t plus s plus a equal to t plus a plus s plus a by definition. So r plus is abelian. It is satisfies abelian group, that r plus is abelian group. So second part, I want to show that r by a dot is semi group. So first closure property is similar to the hypothesis. Second part, s plus n t plus a equal to s plus a belongs to r by a. So by hypothesis it is satisfy closure property. As usual, just now we have verified with respect to addition. You can verify with respect to dot also by associate property with respect to here dot not plus here dot s plus a into t plus a, p plus a belongs to r by a. I am taking s plus a dot t plus a into t plus a. So here s plus here s plus a dot t plus a equal to s t plus a plus p dot a. Here s plus t nothing but s dot here s plus s dot t dot t, s plus dot is nothing but plus in plus to a dot here. You can write dot. You can apply same properties. S plus s dot t plus t, you can written as s dot s dot t dot p, we can imply so s plus a into t plus a t dot p plus a. You can write it as t plus a dot t plus b. Here dot, you are missing dot. So therefore it is easily verify that it is also satisfies here dot with respect to dot. Here is not plus r by is satisfies associate property with respect to dot. Therefore r by is semi group. part 3, let s plus t plus p plus belongs to r by a. I want to verify distribute law. Similarly, just now we verified s plus a into t plus a into p plus a. Here multiply that. Here s plus a, we can adding this t plus p. So if I multiply will there s into t plus p, s2 into t plus written as s into t plus s plus a. Therefore s into t plus a, s into p into play. This written as s plus a into t plus p. S plus a into t plus p, nothing but so it is this into this you can as easily verify it is satisfies so distributed. Similarly, you can multiply t by right side will get equaling this that equal to this. So r by a is satisfies distributed law. Therefore r by comma r by a satisfies all properties of ring. Therefore r by a comma plus is a ring, and this ring is called factor ring. Theorem, Siddhantam, theorem. I am taking that if R is commutative ring with unity, A is proper ideal of R. Show that R by A is commutative ring with unity. So short answer type is very important for examination point. If R by A is commutative ring with unity and A is proper ideal of R, show that R by A is commutative ring with unity. Since R is commutative ring with unity and A is ideal of R, then we have to show that R by A is commutative ring with unity. Let R be a commutative ring with unity and A is proper ideal of R. Clearly, R by A is a ring. Just now already proved that. It is a factor ring. R by A nothing but R places that R belongs to R. Let I am taking that R be an abelian ring. So R be abelian ring, what we know that A B equal to B A for all A comma belongs to R. Or you can write ST equal to TS for all S comma T belongs to R. Here I am using S comma T, that's why I am writing ST into T equal to TS. So I am taking T element S plus A and T plus A belongs to R by A. S plus A into T plus A equal to, I am verifying abelian property for this. So equal to S plus A into T plus A. It written as ST plus A. ST plus A equal to as TS plus A. So since R is abelian, ST equal to TS, just now we define R is abelian, we can written as ST equal to TS. Here by definition of multiplication in quotient ring, you can written as T plus A into S plus A. So S plus A into T plus A equal to T plus A into S plus A for all S plus A comma T plus R by A. Therefore R by A is an abelian. R by A satisfies an abelian property. Next I want to verify R belongs to R. Okay, R is abelian ring with unity. You can written as S into 1 equal to 1 into S equal to S for all S belongs to R. If 1 belongs to R, then 1 plus A belongs to R by A by definition of quotient ring. I am verifying S plus A into 1 plus A equal to S plus A into 1 plus A equal to S into 1 plus A. S into 1 equal to S, just now by above property S plus A. Similarly, 1 plus A equal to into S plus A equal to 1 into S plus A, that equal to S plus A. Therefore, S plus A into 1 plus A equal to 1 plus A into S plus A equal to S plus A. Therefore, 1 plus is an identity element in R by A. Therefore, R by A is commutative ring with unity. Hence, proved theorem. So let Z comma plus comma dot is a ring. I am verifying the factor rings examples. 4Z comma plus comma dot is an ideal. I am taking that ideal of Z comma plus comma dot Z comma plus ring and 4Z comma plus ideal. Z by 4Z is equal to singleton 0. Z by 4Z equal to 0 plus 4Z. Z by 4 at the back we can written as equal to just now R by equal to R plus E such that R belonging to R. Here I am written as R plus 4Z such that R belonging to Z. After getting all values, what we have here 0 plus 4Z, 1 plus 4Z, 2 plus 4Z, 3 plus 4Z. If I write 4 plus 4Z equal to 0 plus 4Z only. 5 plus 4Z equal to 5 plus 4Z only. 6 plus 4Z equal to 2 plus 4Z only. 7 plus 4Z equal to 3 plus 4Z only. And next to 8 plus 4Z will get continue this after all getting after doing all properties we will equivalent this we will get this set only, and Z by 4Z equal to the final set is this. So that means the factoring is this. If I take Z6 additional model 6 and multiplication model 6 is the ring, gendered 3 and additional model 6 and multiplication model 6 is the ideal of Z6 plus Z6 equal to this, gendered 3 equal to the factoring Z6 by gendered 3 is 0 plus additional model 3 comma plus 1 plus gendered 3 and 2 plus gendered 3. So can 1 plus generator 3 equal to 0 comma 3, that equal to 3 plus generator 3. 1 plus generator 3 equal to 1 plus 1 comma 4, that equal to 4 comma generator 3. So 2 comma generator 3 equal to 2 comma 5, that equal to 5 by generator 3. So it contains this element. Prime ideal. An ideal A of commutative ring R is said to be prime ideal if A comma B belongs to R comma AB belonging to A, which implies A belongs to A or B belongs to A. An ideal of a commutative ring R is said to be prime ideal if I am taking that A comma belongs to R, if I multiply the resultant A B belongs to A, then A equal to A or B equal to A. For example, I am verifying Z comma plus comma dot is a commutative ring. I am taking 2Z comma plus comma this ideal of Z comma plus comma dot. So I am taking two elements 5 comma 6 belongs to Z. The multiplication 5 comma 6 belongs to Z and 5 into 6 equals 30, 30 belong into A, right? That means 2Z. So 30 belongs to Z, but 6 which implies 6 belongs to A. Therefore 2Z comma plus comma dot is prime ideal. You can take any element resultant to, if I multiply will get the same result. Okay, so that means 2Z complex can take a 3 into 10, 30, 30 belongs to A. So that means 2Z complex commodity is prime ideal. You can I will take other example. Z complex commodity is commutative ring and 4Z complex commodity is ideal of Z complex comma dot. 2 comma 6 belongs to R. 2 into 6 equal to how much? 12. 12 belongs to A. 2 does not belongs to A and 6 does not belongs to A. Therefore 4Z complex comma dot is not prime ideals. The resultant to 12 belongs to A and 2 comma 6 belongs to Z, but 2 does not belongs to A and 6 does not belongs to A. Therefore 4Z complex comma data is not prime ideal. Similarly, you can verify that 3Z, 5Z, 7Z, 11Z dash are prime ideal. If I write here pz comma plus comma dot where p is prime is a prime ideal. So 6z comma 8z comma 9z comma 10z plus dash or not prime ideal. So if I here I am writing here not prime number, I am taking here not prime number, here I am taking prime number. If I take prime number, it is prime ideals. If I not take or not prime ideal. Oh, I am verifying other example. Z6 addition model 6 multiplication model 6 is commutative ring. Generate 3 addition model 6 and generate multiplication model 6 ideal of Z6. Generate 3 equal to 0 comma 3. 3 belong to generate 3. 3 into 5 equal to 15 mod 6. That equal 3 belong generate 3. 3 into 1 equal to 3. 3 belong generate 3. You can take the 0 0 generate 3. 2 into 3 equal to generate 3. 3 belongs generate 3. So 4 into 3 equal to 0. That means 3 belongs generate 3. So therefore this is the prime ideal. Generate 3 is prime ideal. So you can verify that generator 4 also 0 4 0 4 2 0 belongs to 6. 2 into 3 equal to 6. So that means 2 belongs generator 4. 4 belongs generator 4. You can take that 2 into 2 equal to 2 belong 4 so 2 also belongs generator 3. If I take that 4 into 4 equal to 4, that equal generator 4 belongs generator 3. Therefore generator 4 also prime ideal. If I take generator 3, singleton 0, singleton 0 belongs generator 3, 2 into 3 equal to multiplication of 6 equal to how much here? 6, so 6 mod 6 for 0, but 2 does not belong generator 3 and generator 0, 3 does not generator 3, 4, singleton 0 is not prime ideal. If I take generator 5 equal to this, that equal Z5 is prime ideal. So, right, Q complex comma dot is commutative ring and 0 comma or ideals of Q complex comma dot. Q comma 0 singleton 0 comma Q complex are prime ideals. If I write here in this case with respect to here, first thing is 0 comma 0 equal to 0 into 1, 0 belongs to singleton 0, 0 into 2 equal to 0 belongs to, right? If I take 0 belongs to G set, you can multiply any element, we will get 0 into that number equal to 0 only. That means 0 belongs to singleton 0, singleton 0 is prime ideal in this case, Q complex comma dot. So Q complex comma dot prime ideal is also prime ideal. R complex comma dot is also prime ideal and C complex comma dot also is prime ideal. So thank you for watching this lecture 11 on prime ideal and quotient rings.